This slide shows the principle of traffic signal operating characteristics. It includes several parameters such as startup loss time, maximum flow rate, and end of green. You will see while the headway increases from 2 seconds to 3 seconds, the maximum flow rate will decrease. While it goes up to 4 seconds, the maximum flow rate continues drops. The general idea is to dynamically adjust parameters including above to optimize the maximum flow rate. The algorithm is based on high-resolution perception and control data, which is in the frequency of 100 milliseconds, supports more than 100 states and events. Different algorithms rely on different detection data. Some of them will need thorough data combined with different locations, which will be difficult to install and also cost a lot. Now algorithms focus on presence, stop bar counts, and yellow-red actuation, which locates 50 to 100 meters perfect matched with video detection, which also support easy installation and save investment. This diagram records all vehicle presences during the whole day in one detector. X-axis is duration of the time, and Y-axis is cycle. Each blue dot is the presence of the vehicles. It also records the start moment of green and red. The discrete distribution of the dots shows the traffic control efficiency. The higher the density of the dots is, the higher efficiency we will have. The real-time vehicle arrival analysis integrated with phase response states reflects the overall performance of signal control across different traffic conditions. From this diagram, you will see part 1 is morning peak. It adopts fixed cycle control mode. However, the dot density becomes small while close to red light on because the cycle is too large. This is set manually. Part 2, normal time. It adopts the adaptive control which get good efficiency. Part 3, and for peak hour in the evening, it changes to fixed cycle again, but the saturation is high and the green time has reached the max. This diagram is to analyze the phase saturation. The red part means how many green time has been used. So the ratio between red and green is the saturation. The higher saturation means a higher traffic efficiency. In this slide, you may see that under the adaptive control mode, the saturation is highly improved through shortened green time, so-called max out and gap out. So, according to both the phase saturation and vehicle arrival characteristics analysis, we can differentiate the traffic state into three. First, saturated and supersaturated. Under this situation, we use fixed cycle or CLF coordinated control to reach a traffic equilibrium and traffic congestion mitigation. Number 2, not saturated or normal state. We use adaptive control to reach a maximum capacity. Number 3, low and discontinuous. We use VA control or inductive control to realize minimum delay. This is the major algorithm for control mode auto selection. The algorithm control model includes the adjustment of phase, cycle, split, and offset. The adjustment of phase is to maximize the phase green index called GI. The GI is calculated in following formula related to XG, effective green utilization time, TG, allocated effective green time, and V, designed capacity. By analyzing the green index GI of the conflicting approaches at an intersection, we can compare the GI values of all conflict directions under any signal control scheme. By examining the variation in green index across different time periods for the same movement direction, we can evaluate the impact of signal timing adjustments on intersection capacity at different times. Now algorithm is to adjust the cycle and the split to optimize the GI performance for each phase. This slide shows how to adjust the offset to realize corridor or region control. We need to identify a key intersection. Based on this key intersection, to adjust offset of coordinate adjacent intersections along the corridor to achieve a synchronized corridor control. Here we summarize null algorithm advantages. Firstly, null algorithm is based on a 100 millisecond high-resolution perception with rich states and events, fully meets all kinds of complicated traffic situations. It sets up a control model, relies on the detection data of 50 meters around the stop bar detection, which perfectly fit video detection with easy installation and low implementation cost. Secondly, the algorithm combines the advantages of both SCATS and SCOOTS systems. It can do control mode selection according to the phase saturation and traffic vehicle arrival analysis, not like SCATS system need to preset plans for selection. It can also realize automatic dynamic control plan generation by adjust the split cycle and offset and maximize the phase screen index performance. Beyond Scoot, we can realize mode shifting while traffic is saturated, not like Scoot which will have limited performance while traffic gets saturated. Here you see the benchmark of our system compared with SCATS and Scoot. It supports plan generation by optimizing split, cycle, and offset, also support control mode auto selection. It just combines the advantages of both SCATS and SCOOT.